Good afternoon, everybody. Just to correct the factual accuracy slightly there about Douglas Adams, I didn't know him, but it's one of these analytical things of degrees of separation, which is that my wife's cousin dated Douglas Adams' sister and he lived 200 meters away from us. So that is my one claim to fame, and somehow I've built a career on it. Today, I want to talk to you about AI. It is a subject which is massively hyped and around which there is a huge amount of confusion and uncertainty. We know it's a good thing. We've been told about the potential it has to transform the world, to transform people's lives. But even if people believe that there's value in it, how do you get that value? So what I want to talk about today is AI in the IoT and industrial space. I want to give examples of what people are doing and the value they've been getting from it. But I then want to talk about how do you do it? How do you get there? What does it take to actually ensure that your first efforts in AI in IoT are going to be successful? At the root of it all, of course, is data. And you might have heard that phrase, data is the new oil. It's been overused by many different people. I had some difficulty tracking back the original source of it, but apparently the first person quoted on this was Clive Humby of Dunnhumby Associates, who did the loyalty card scheme for Tesco. Not something you could associate with oil. But it's actually a very appropriate analogy, because like oil, it is something that has huge value. But also, like oil, it is something you can't easily use in its raw state. It needs to be refined. Things need to be done with it. It needs to be analyzed, and techniques and approaches like machine learning need to be applied to it. Now, when we take it into the IoT space, we have an embarrassment of riches as far as data is concerned. I've heard many estimates of there being up to as much as 6,000 exabytes of IoT data generated every year. But of that, how much is used? How much just fades away? How much gathers dust in archives? And if only 12% is used, think about the untapped potential. What could you do if you were able to take that other 88% and find a way of putting it to use and getting value from that too? Suddenly, whole new horizons are opened up. As to what you can do with it, you take the data and you apply analytical techniques to it. They let us do a range of things. They let us look back and look at the current state of things and describe what is going on. More interestingly, they let us understand enough about the data to be able to look forward. We can apply predictive analytics to get accurate and robust and reliable predictions of what is going to happen. For example, when a machine is likely to fail. And we can take that further into prescriptive analytics, where we don't just say what is going to happen, we say what is the right thing to do about it, or to do to prevent it, for example, in the case of machine failure. And with AI being a very vague term, an overused, multiply defined term, I'm going to say, for the sake of what I'm talking about here, those rightmost two parts, when it becomes predictive, when it becomes prescriptive, is when we can call this intelligent, when we are using machine learning algorithms to actually create machine intelligence that can be applied. That, to me, constitutes AI. Now, where do we use that in the industrial sector? Well, the vast majority of cases are in the area of predictive maintenance. When something fails, something has got to be done. And any company that operates equipment, that manufactures and sells equipment, that depends on the output and performance of equipment, this is a crucial issue for them. And there are different stages of maturity in how they use it. So every company has gone through this phase of reactive maintenance, what we describe as break fix. Something stops working and you rush out and fix it. It has to be done, but it is impossible to plan around. It is expensive. It is disruptive as machines become unavailable. So many organizations, therefore, move up the ladder to preventative maintenance. And just to confuse things, sometimes this is labeled as predictive maintenance, because there is some statistics at the heart of it, but very simple statistics. It's mean time to failure. So they're calculating that, for example, if this type of valve on average, fails at 30,000 hours of use. You inspect it religiously at 25,000, and you always replace it at 28,000. And that's fine, but it makes no differentiation between a valve that is only used 1/10 of the time in a nice, simple environment in this climate here, and one that is used in the middle of the desert to 95% capacity per day. Those are going to fail in completely different ways at different times, but a simple average is all that is applied to them in preventative maintenance. So then, organizations move on to condition-based maintenance and monitoring to try to get closer to the individual piece of equipment. But here, you're really looking for very obvious signs that the thing is failing. If it's rotating equipment, it's rumbling more, it's getting hotter. And when these things happen, you're often very, very close to failure. The thing is broken already. So we would term real predictive maintenance as being where you take into account all the data about the machine, and how it's operating, its environment, its level of usage, and so on, and you make an accurate prediction of when and how it's going to fail that's long enough in term to do something about it. We also can not just keep equipment running with predictive maintenance, we can also use the same techniques to optimize, to make the machines run as well as possible, to do their job better if they're manufacturing something, to produce things of higher quality, or whatever the machines are doing, maybe try to do optimal energy usage, so they're burning less energy as they go. And the places where these approaches can be applied are many and varied. I'm going to just talk through some of these for you just now. And it can be anything, as I've said there, from turbines to printers. Let's take turbines. So Israel Electric is responsible for generating most of the electricity for the state of Israel and had very good state-of-the-art condition monitoring in place. And the effect of that was they could tell when a turbine was going to break, but only with 30 minutes lead time. That is just enough time to phone home and say, have we got candles in the house? Because the lights are going to go out. There is no time to prevent an outage for that. By taking an AI approach, a predictive analytics approach, they were able to get that lead time up to 30 hours. No longer 30 minutes, but 30 hours. That is enough time to either preventatively maintain the turbine, to prevent the failure happening, or to arrange alternative power sources while it's down. And they were able to to eliminate the vast number of outages, keep the lights on. They reduced their overall costs of maintaining the equipment by 25%, as they no longer had to reboot power stations so often. And the intelligence also found useful facts for them. For example, it found that one particular failure mode didn't stop the turbine, but when it happened, it burned far too much fuel. And just by the analytics and the predictive models recognizing when that was going to happen, they were able to make a saving of $70,000 per turbine per year. Why have I paired turbines and printers? Because there's two extremes. I've given you the case of one turbine being a critical piece of equipment for keeping the lights on in a country. Now imagine a printer, a laser printer, okay? But think about when you have whole fleets of printers working together. Because in many countries and many organizations, that's how they're managed. You might have a particular company managing printers for several departments of the US government, hundreds of thousands of printers, and all of them feed data back. The Internet of Printers is one of the earliest examples of the IoT. They've always been heavily instrumented, but in the past, all that has been used for is billing, basically. But companies have now latched on to the ability to layer predictive services on top of that. And something as simple as predicting when the toner will run dry. So who's changed an ink cartridge on your home printer recently? Do you think it was really finished? Nah, maybe not. Any idea how much ink on average is left in printers, in printer cartridges when they're changed? No guesses? The supposed industry average is around the 10% mark. When companies involved in this work actually took lots of printer cartridges and weighed them, it's actually in the upper 20s. Now that's fine if the people you're providing with print services get charged every time you change it. But if you're, as they are today, doing it as pay per page, then every time you change it, it costs you money. And so we've found organizations offering services across massive numbers of printers to optimize the time that they change consumables. Huge savings to be made from what seems like a trivial type of application. Transportation. Rolls-Royce were the first aero engine manufacturer to introduce power by the hour. Pratt & Whitney followed them, being able to predict main engine failure modes almost a year in advance, in plenty time to do something about it. They claimed that this allows them to extend the life of an aircraft engine between major refits, and a refit can cost up to $10 million, from something like 4 to 5 years on average to 6 years. A huge saving, and at the same time reducing the maintenance cost by 20%. Why? Because they are getting an earlier warning and are able to maintain the engine before it degrades and is damaged. In trains, a major US railway operator moved from a system where they had state-of-the-art condition monitoring. They have detectors, sensors on the train, at the track side to see how the bearings on the wheels are rumbling or heating up, and they would then have those alarms come back to a control center in time for them to do something. But the something was an action like stopping the train, or slowing it down to 20 kilometers an hour until they could service it, or decoupling the cars from it at the next station. And because the train isn't the only thing on the network, it stopped everything else. It was disruptive. Again, the benefit of going to a truly predictive AI-based approach, they could predict these alarms with 98% accuracy 7 days in advance. It allowed them to plan for the next week which trains and carriages they would take off the tracks for maintenance so the failures wouldn't happen and they avoid disruption. In cars, Honda can predict failures of their electric vehicles so accurately that they can contact you if you have one without you even knowing there's a problem. With a 3-month lead time, they might ask you to bring it in for a little update, and they actually fix the problem that would bring it to a halt without you ever realizing there was an issue. BMW, in their casting plants, when they produce cylinder blocks, they have reduced the bad casting rate by 80%, the reject rate by 80% in 3 months, by letting predictive analytics and AI go into the data and finding out what the root causes were of the bad castings and eliminating them. Oil and gas wells. Santos, an operator in Australia, used analytics extensively, and they do this on a highly distributed operation. So their gas wells are something like 5 days drive out in some of the most hostile environments in the world, and then hours of driving between them. And apart from trying to keep these things going and efficient as possible, there's a health and safety issue here. You don't send people out to that environment more often than you can help. You need to be able to fix things reliably the first time. What they're able to do is when there is a problem with the consumables, like some of the types of liquid that need to be kept and used at these things, they can preempt that and do optimized runs to replenish it. When there is going to be a failure in the on-site electronics and the power, they can, again, intervene in time to prevent that. It's a project which their estimate of initial success was something like $500,000 a year. But they made, again, the machine learning algorithms made one particular finding. And they found that a lot of the batteries in the remote operated wells were failing much sooner than they should have done. And actually tracing that back, they discovered poor practice among the engineers fitting them. Just by correcting that mistake and extending battery life, the return on investment of the project has gone up to something like $3 million a year. Mining, an area where equipment is hugely critical, and the manufacturers and users of this equipment are all heavily into predictive maintenance of their equipment. The particular product there comes from one particular supplier who already offered a monitoring system where all the data flowed back to their headquarters in the US, and they tracked what was happening with the equipment their customers were using on sites. By adding a predictive layer onto it, they can optimize maintenance interventions to keep the equipment running, and they combine the data on the equipment health even with things like the plant schedule. So they know when, for example, they can schedule a fix to a particular piece of equipment during the operator's lunch break to avoid any additional downtime. Making steel. Making steel, rolling out steel sheeting is an expensive, complex, and hot and dangerous business. What happens is you take a lump of steel that has been produced, an ingot of steel, it goes through a successively finer rollers, and it ends up in a single sheet, in this particular factory, 2.5 kilometers long, and gets rolled up at the end. Now, things can go wrong, but when they do, it's not nice. You have 2.5 kilometers of steel wrapped around the rollers in your mill, and it's solidified into hard steel. You have a big problem there. And what had to be done with predictive analytics was predict when that could happen. Now, the data was very fine-grained, real-time data. Every 50 milliseconds, they could read all sorts of points of temperature across the steel. But just because you have the real-time data doesn't mean a real-time intervention is the right thing to do. Because if you know it's going to fail now, and you stop everything, you're still left with 2.5 kilometers of steel setting, solidifying inside your mill. So what this had to be deployed as is predicting when the mill is getting in that state, and before you start a potentially risky run, you go and change rollers 17 and 23, or whatever it is. And finally, we are seeing it also applied to buildings. We are seeing people try to optimize the energy usage of buildings, the comfort and usefulness of buildings for the people who occupy them, and the operations, things like maintaining the buildings. But more and more things you see and encounter today are not just IoT connected, but are smart in buildings. If you take Kone, for example, all of the data from their elevators and escalators worldwide streams back to Finland, and AI is applied to it. And there is a website you can log on to called machineconversations.com, where you can watch these lifts, these elevators, talking to the AI about their health and how they're doing. And being a worried elevator, being reassured is going to be fine. But an engineer is going to come and fix it if necessary. So, those are just some of the benefits that industrial organizations can get from applying AI to their equipment in this fully connected, IoT-enabled world. How can you go wrong in trying to get started and apply AI? Well, the first thing is you can get overexcited about the data. Go back to 2010, and we had the wave of big data was coming to us first of all, which then has gradually evolved into this wave of AI. But the story that was often coming to people then was, you've got fantastic value in your data, dive into it with these cool analytical technologies, and you will find something interesting. Well, if you dive into your data lake, the most likely outcome is you're going to drown, because there could be any number of patterns and relationships in the data that are statistically significant. Very, very few of them are actually significant to the business and the operations. So rather than start off with the data and throw some cool technology at it, always work backwards. You always need to start off with a business focus. What are our business and operational imperatives? What decisions do we need to improve to drive better outcomes in them? Therefore, what analytics and what intelligence do we need to drive those better decisions? And then what data does that need to be applied to get us to that point? So it's always a pull from the business and not a drive from the wonderful data and exotic technologies that you have. Decide where you're going to use it, what it's going to do for you, where you'll plug it in, and then work out how to apply AI and the right data to get that desired result. With this being such a wonderful transformational technology, again, you will hear people talk about AI and tell you, you've got to embrace it. Use it everywhere. become an artificial intelligence-enabled company worldwide. And I think that's meant to be the big bang there. You can hear sort of choirs of angels. You know, hallelujah, we can transform. But just remember, if you think about transforming like that, there is more than one kind of big bang. Okay? When you try to change everything at one time, almost inevitably something really unplanned for and unpleasant happens. So rather than take a big bang approach, rather than try to jump to exhaustive use of AI across your organization and decision making, it's about quick wins. It is trying to pick the low-hanging fruit. Okay? It's a case of enumerating, listing out the different potential use cases and areas, and evaluating them, partly against how much value they have, but also against how quickly and how well can you do them. So for example, there might be a wonderful value opportunity you see that could make you billions, but your data might not be ready for that, or it might be operationally hard to use the results of it. Go for the ones, first of all, that are doable today and make a direct, measurable value contribution to your business imperatives. Don't throw data over the wall. Ever since people first talked about data mining before it changed to predictive analytics, some people were saying, it just needs you to give it to the smart guys. Throw it over the wall to them, they'll throw back results. It doesn't work like that. People doing the analysis cannot be dissociated from the business. So maybe, there's a problem with failure of trucks. And maybe data on the whole fleet gets sent across to these smart data science guys, and they spend 3 months building a failure model, and it gets 90% accurate. They tune it for 2 more months, it gets 93% accurate, and they go back to the operators and say, here's our success, isn't it wonderful? And the operators look at it and say, really sorry guys, but the 7% you got wrong just happened to be the only trucks we really care about for this. Okay? Never disconnected from the business. It has to be a team that bring together the business knowledge and the AI and analytical expertise. And that brings me to the topic of how AI is done. So data science. Is there anybody here who would call themselves a data scientist today? Okay. Data science is official. I saw a hand twitch there. So data science, officially the sexiest job of the 21st century. That was from Harvard Business Review back in 2010 or 2011. And it's done a bit of damage. I mean, it's great that those skills are valued, but it's made it up into some sort of superstar with unmatchable, detailed skills. And what you tend to get today is most data science is a really skilled expert. But they work at the individual level, they work at the level of code, and they do one-off, beautiful, handcrafted analysis. It is artisan work, it is handcrafted work versus industrialization. And the reason I've drawn a picture of this guy hammering a piece of hot metal is, to me, currently, most data science is like manufacture was before the Industrial Revolution. So you had these craftsmen making things the same way they had for the last 1,000+ years. This person with all their expertise, their lifetime of experience, hammered this piece of hot metal very skillfully, sold it to you, and moved on to the next one. It didn't scale. Then what happened? In the late 1700s, the principles of mass production came in. How to break down the manufacturing process into steps, and how to execute those steps automatically in factories powered by new power sources like the steam engine, for example. And so today, you have automated factories turning out millions of Toyotas or whatever. Now, the expert hasn't gone away. But the expert no longer creates and builds every predictive model themselves and applies it and monitors and manages it. But what they do instead is they're using their knowledge and expertise to build the processes that can do that at a level of automation way beyond human capacity. So that is something I'd like you to take away today is, as you're embracing data science, if you're going for the level, the manual approach, the crafts approach with one-off hand-coded analysis, that doesn't scale, and it's going to need to scale according to sources like McKinsey, who are measuring the potential demand for people with these skills. Okay, we're simply not going to have enough for them to execute what is out there. So instead, we've got to get to this stage. We've got to have an approach that is scalable. That means that a lot of it is automated. A lot of the repetitive work is done by the machine rather than the person. It's got to be industrialized, bulletproof, rugged, and it's got to bring in domain expertise. It's got to integrate the business knowledge and has to deliver into the business. It's not a science project park off to the side finding interesting results. It is something which has got to end up delivering operational systems that, for example, on an ongoing basis, monitor 2 million devices and alert in good time when any one of them is likely to fail. That, I hope, has given you some idea of what AI can do in the industrial world, and if you're getting into it, some of the steps that you should take to ensure that you go about it the way that is most likely to get you results. I'm very happy to talk to you about that more. I will be around for the rest of the day. Also, the rest of my colleagues at Houston Analytics will be on the booth over there. But I just want to finish by saying, where can this take industrial use of AI? What can it really do for the IoT connected world? Well, it gives us machines that will work more of the time. They won't fail so often, so they'll be more reliable, they'll be more highly available. They'll be efficient in what they do. They'll be efficient in the use of raw materials if they're in manufacturing. They'll be efficient in energy, for example. They will get better at what they do. They will be autonomous. They will need far less human intervention to set them up, to control them, and such like. They will be flexible to a larger extent as situations change around them. And overall, all of these factors will make them increasingly cost-effective to own and to operate. They will be better partners for us in these in our business, these AI-enabled machines. But what also should not be overlooked is they will not just do their job as a dumb machine, doing their part of the process. More and more, they will contribute to the optimization of the process they support. If you're making paper, they'll help you make higher quality paper more economically with less energy, for example. They will make your processes better, and they will be more adaptive. Automation is something that I've mentioned a couple of times, and it is very important, bless you, when we come to look at how machines operate in industrial processes. And I'd just like to make a distinction between traditional types of automation and where we can go with it, which is when real AI-based optimization is brought in. So if you look at what is typically done in industrial and process automation today, it is fixed. There are rules defined that say, in this particular situation, the machine must do this. They don't change. They can recognize, of course, the situations where rules should be applied, but basically, that rule-based execution happens and is unchanged. When we bring in AI, we can do what we might call point optimization. So systems can learn, instead of us hand-coding the rule, they're learning what to do, learning about the risk of failure and so on, and each decision can be made based on the current data. But also, because it's based on machine learning, these systems can go on improving. When things change, when new product configurations are needed, when equipment ages and is likely to perform and fail in different ways, it means those systems can be kept up to date. But still what it's doing is injecting little bits of intelligence at different parts of the automated process in a richer, more powerful, and more flexible way, but it still isn't a holistic view. The holistic view comes with optimization, where AI can give you the right things to do in each of the decisions that needs to be made, but an optimization engine can then run across all of those different AI-based recommendations or findings and all the different scenarios where they could play out, run that against objectives like minimizing energy usage and maximizing production or whatever it is, constraints, for example, of how much you can run the plant between shutdowns and so on. And by running these things, having the intelligence systems go off and iterate through thousands of opportunities, you end up with the entire process optimized. I think that is a situation where we're getting close to today. I think it has huge opportunities for smarter industry based around IoT data and artificial intelligence. And I hope what I've given you today is some food for thought. As I said, I'll be delighted to talk to you later on. I'll be around today or come over to the booth. But in the meantime, thank you very much for your attention and enjoy the rest of today. Thank you.